Sinclair. I'm one of the computer architecture faculty here. And of course, as with every other group, we have some slides that I'll talk through. But before I get there, the biggest thing I want to make clear to everyone is if you're someone who's interested in building these systems that you've heard so much about today, and you're someone who's interested in working on the cutting edge and figuring out what the next generation hardware, or even what the next generation hardware and how it interacts with operating systems, or compilers, or programming languages, or security, or any of the other areas you've heard about, architecture at Wisconsin is the place in the area to come and do that kind of work. And so collectively, the six of us who you see there are the folks here who are working on those problems, and what I'll tell you a little bit about today is how we're working on problems across all those different kinds of spaces within architecture, as well as reaching out into those other domains that I mentioned. So the six of us are Mark Hill, Miko Leposti, Karusan Kurlingam, Josh San Miguel, myself, and Gary Sogi. And Mark is going to be becoming emeritus starting next year. But again, the sign of is both that we have a mix of younger people like myself, as well as people along the entire spectrum who've been doing cutting-edge, groundbreaking work in designing future processors, including the kind of things that all of you have in your pocket, or on your watch, or in your backpack right now. And really, where this started from is that we had an evolution, or maybe a revolution, in how we designed processors. And a lot of this work that happened maybe before many of you were born was looking at uniprocessors. And this was maybe the halcyon days, where we got 34% annual growth in terms of how fast we could make these processors without having to add any additional money in terms of consumer cost or making it consume more power. And then a lot of the techniques that enabled this were driven by work done by Sogi, Smith, Goodman, Hill, and Wood here at Wisconsin. And that has continued as we exited that sort of halcyon days where we could continue doing that and moved on into the ongoing transition of the multi-core world, where we could no longer make one single processor faster and faster, or better performing without increasing power. And so that meant we needed to start looking at new challenges in terms of how you connect many of these processors together, how you communicate between them, how you synchronize between them, and how you maybe handle the fact that you can't power all of those processors at once because doing so would melt your chip, for example. And again, here at Wisconsin, we've been driving a lot of the foundational and fundamental work in that area across our research groups. And the big question is, where is that going to continue? As many of you may know, the future you might have seen a few articles about the end of Moore's Law. I actually have been doing a study over the past few years about the number of articles on the end of Moore's Law, and it turns out that the number of articles about the end of Moore's Law also follows Moore's Law. If you're interested and you want to meet with me later today, I'm happy to show you that graph. But really what that shows is that we're at a great inflection point, which is a wonderful time to be doing research in the field. A time where basically no crazy wild idea is going to be taken for granted. We are looking at lots of revolutionary and foundational work that again can propel our community forward. And really all the other areas that you've heard about today are going to need to continue relying on our computers getting faster, more powerful, hopefully less energy hungry, and so on. And there's no silver bullet to solving this problem, but two of the ways that we here, as well as the community, are exploring are looking at ways to improve parallelism, as I mentioned before, as well as ways to exploit heterogeneity. For example, your smartphone that most of you have in your pocket has something around 40 to 60 different kinds of processors nowadays. And figuring out ways to make those things programmable, ways to make the different processors communicate with one another, ways to make them secure so that they don't leak information that, like your bank account, for example, are very difficult, especially given the power constraints that these kinds of systems have. And so the work we're doing here, like I said at the beginning, is really cutting across layers. We're looking at not just hardware, but the operating system, the compilers like LLVM, tools like Gem5, which people like myself and Mark Hill and David Wood before me have been driving the work to make them representative of these next generation chips. So there's a lot of opportunities here for you to come and contribute and help move this kind of work forward. And as I alluded to at the beginning, really what this all highlights is how architecture research in Wisconsin has both a very strong history, which I'm not going to go over all the details of, but we've been foundational in terms of the processor architecture itself, looking at ways to optimize the memory system in a whole host of different ways, as well as, again, building a whole host of tools that are widely used across the community. And I know from talking to a few of you already today, you use at your universities where you might have been doing research already. And I think there's a real power to having that kind of influence where the entire community uses those tools and get the benefit from. Similarly, moving forward, currently we have several large groups and projects with a whole bunch of grad students who are working on the interesting problems of the day, and as well as having been recognized with awards at all the different stages of our career, including Professor Hill, Professor Sohi, and so on, having the Eckert-Mockley Awards or the Books Award, which are the highest awards you can get in computer architecture, as well as being fellows like IEEE and ACM, and so on, as well as people like Josh and myself, who are at the beginning of our careers, who have been getting awards that are given to people as they're graduating from grad school. And perhaps unsurprisingly, our students have gone on to a lot of success, both in industry and academia. We have a whole bunch of people who are now doing tons of cutting-edge work of their own, some of whom are your advisors, who you guys are already working with or have worked with in the past. And this goes both within the US as well as elsewhere in the world, in India, in Europe, and so on and so forth. And similarly, our graduates have gone on to design the foundational behind the design of many of the chips that you may have heard about or used across all kinds of different spaces. And really, we'd like it to have you come here and continue that tradition and continue that legacy and continue pushing forward with the kind of top accolades and awards that we've done in the past. So to briefly give you a summary of what all of us are working on, what Mark Hill has been working on in recent times is looking at ways to optimize virtual memory and ways to handle new foundational things like persistent memory. Because these kind of innovations, as we continue to scale up and scale out, require sort of fundamentally changing the way that we think about these systems. And moving forward, what he's looking at are how things like heterogeneous systems and how security are impacted by these changes that we're facing. Karu, he works on technology-driven architecture, and this includes things like looking at programmable accelerators as well as stream data flow acceleration. And really what Karu is doing is he's looking at things from the circuit level all the way up to the algorithmic level, which is what he calls a vertically integrated design. Professor Sohi, as some of you may know, has been fundamental behind a lot of the work in speculative multi-threading and its variants. And what he's looking at now are twofold. First, he's looking at ways to handle this heterogeneity that exists in these systems and find ways to improve the programmability, as well as trying to find ways to improve the security of these systems. As many of you may know, things like Spectre and Meltdown that have come out in recent years present a very significant challenge that kind of fundamentally alters the way that we've been designing these chips and providing security. And Professor Sohi is looking at ways that we can improve that. Miko is looking at a whole bunch of things across a wide range of areas in the field, going all the way from looking at novel low-power cache coherence or interconnects down to doing biologically inspired computing, including the spiking neural networks that maybe we believe, or not we believe, but the community believes are more representative of how the brain actually works and has significant advantages over the machine learning kind of approaches in terms of power and energy efficiency, for example. My group is focused on general purpose GPUs and heterogeneous computing, and this takes a couple different forms. For example, looking at ways to optimize coherence and consistency in data organization. And what my group is working on right now is looking at these next generation applications that don't necessarily run well in current systems, but with some tender level of care can be optimized for future systems. And so we're optimizing and building the tools to study these kind of things, as well as looking at the hardware, the software, and the algorithms for these emerging applications. And finally, Josh is looking at energy-centric computing. So if you're somebody who is really interested in edge computing and you like working with sensors and you're looking at very low power devices that maybe need solar power, for example, or maybe you can only communicate once a day, Josh is doing lots of really cool work with approximate computing, energy harvesting, intermittence, from the circuit level all the way up to the programming languages to try and deal with this emerging and challenging domain. So again, similar to other groups, we have a website that documents all this kind of stuff I told you about and more. But hopefully you'll consider coming here and adding to both the strong past and the strong present and future of architecture research at Wisconsin. And the last thing I want to mention is, for those of you who are interested, we'll have a meeting with our students from 3 to 4 on the shelf, which is as soon as you walk into the CS building from here. It's right above you. So you're welcome to come and meet our students, learn about the kind of work they're doing, what it's like to be a student working with us on research here. And of course,